Welcome back to another deep dive, part of the All Sorts podcast universe. This is where we take the information you provide, articles, notes, research, and really unpack it together.
Yeah, we act like guides, sort of charting a course through all that data you've gathered.
Exactly. Think of these deep dives as, well, like focusing lenses. We take complex topics, bring them into sharp relief, find those connections, and hopefully make learning more engaging, maybe even unlock some new understanding for you.
And today, that lens is aimed right at solid-state drives, or SSDs. You know, the things making our computers feel so much faster these days. We've got a great stack of sources from you covering the tech, how to analyze it, and crucially, how to optimize these things.
So our mission here is pretty clear. Extract the key insights. What makes SSDs tick? How do you keep them lightning fast? And what does endurance actually mean for their lifespan? We want to pull out the practical stuff.
Sounds good. So where should we start? Maybe the absolute basics. SSD versus the old spinning hard drives.
Yeah, let's do that. It really comes down to what's inside, doesn't it? The traditional hard disk drives, the HDDs, they're mechanical.
Right. You got those spinning platters like tiny records and an arm that moves back and forth to read the data. Lots of moving parts.
But those moving parts are the bottleneck for speed. Solid-state drives, though, totally different beast, no moving parts at all.
Exactly. They use flash memory, specifically NAND flash memory, to store data electronically. It's all solid state, hence the name.
And that one difference, no moving parts, that's what unlocks all the advantages we love about SSDs, like the speed.
Absolutely.
Yeah.
Because there's no physical head zipping around, accessing data is way faster, much lower latency, so your whole system feels snappier, apps load quicker, files open, almost instantly.
Plus, they're silent, they handle being bumped around much better, great for laptops, and they usually use less power, too.
Definitely. But like anything, there are trade-offs, or at least there have been historically. Cost is the big one. Per gigabyte, SSDs are generally still more expensive than HDDs.
Though that gap is closing.
It is, yeah. But the sources mention, if you need truly massive storage, like for archiving, HDDs still offer huge capacities up to 36 terabytes maybe in 2025. SSDs can get huge, like 100 TB in special cases, but consumer drives often top out a bit lower than the biggest HDDs right now.
So HDDs still have a place for just bulk, cheap storage.
Precisely. The other thing with SSDs is that the flash memory itself has a limited lifespan. Every time you write and erase data, the cells wear down a tiny bit. That leads to this concept of endurance.
We'll definitely need to dig into that endurance piece.
Yes. Yeah, and also related to that, if a drive is really worn out, some sources suggest it might not hold data reliably for super long periods without power, maybe less reliably than an old HDD for like long-term archival storage in a drawer.
Okay, which is why you often see those hybrid setups, right? An SSD for the operating system and programs for speed, and then a big HDD for photos, videos, all that stuff.
Best of both worlds, really. It's a very common and effective setup. Now, you mentioned NAND flash is the core. Should we maybe unpack that a bit? Because the type of NAND flash is key to performance and that endurance thing.
Okay, yeah. Is all NAND flash created equal?
Not at all.
Yeah.
And understanding the differences, well, one of those key nuggets from the sources, it basically comes down to how many bits of data get stored in each tiny memory cell.
More bits per cell means cheaper storage.
Cheaper storage, higher capacity on the same chip, yeah. But it also generally means lower endurance. The cells wear out faster and sometimes slower write performance, especially sustained writes. The source is laid out like a pyramid.
A pyramid? How so?
Well, at the top, the peak, you have SLC single-level cell. Just 1 bit per cell, simple on-off, 0 or 1. It's the most expensive, lowest capacity, but also the most durable and often the fastest for writes.
Okay, top tier. Got it.
Then you step down to MLC multi-level cell, 2 bits per cell. Needs to distinguish between 4 voltage levels, so capacity goes up, cost comes down, but endurance is lower than SLC.
And the pattern just continues down.
Yep. Next is TLC triple-level cell, 3 bits per cell, 8 voltage levels, even higher capacity, lower cost, medium endurance. This is super common in consumer drives now.
Okay.
And at the bottom of the pyramid, the whitest base is QLC quad-level cell. 4 bits per cell, 16 voltage levels. This gives you the most storage for your money, but it also has the lowest endurance rating and can be slower for writes once its cache fills up.
Okay. So that cheap, massive SSD I might buy is probably QLC. And while it's great value, it won't handle, say, constant video editing writes for as long as a maybe smaller, more expensive TLC or MLC drive might.
That's exactly the trade-off. For most everyday users, honestly, even QLC endurance is usually more than enough. But if you have a really write-heavy workload, knowing this helps you choose. Maybe investing a bit more in TLC makes sense for longevity in that case. Oh, and the sources also briefly mentioned things like 3D NAND, which is about stacking cells vertically to get more density, and even other tech like 3D XPoint, which uses a different method, entirely electrical resistance, aiming for even better speed and endurance.
Right, the tech keeps evolving. But let's stick with that endurance concept for NAND flash. You mentioned PE cycles. How do we actually measure how long a drive should last?
So endurance is basically the manufacturer's warranty for how much data you can write to the drive over its expected lifespan before those cells start wearing out significantly. Each write and erase counts as one program erase, or PE, cycle.
And the key metrics are DWPD and TBW. Those letters keep popping up.
Exactly. Those are the two main ways it's measured. DWPD stands for drive writes per day. You see this more often on enterprise drives where the workload is predictable. It tells you how many times you can write the drive's entire capacity every single day for the duration of the warranty, usually 3 or 5 years.
Okay, so like writing 1 terabyte every day to a 1 TB drive for 5 years.
Something like that, yeah. The other metric, more common for consumer drives like in your laptop, is TBW terabytes written. This is simpler. It's just the total number of terabytes you can write to the drive over its entire warranty period.
So a 1 TB drive with a 600 TBW rating means I can write a total of 600 terabytes before it might start having issues related to wear, according to the warranty.
Correct. And 600 terabytes. I mean, for a typical home user, that's a lot of data. You might only write a few terabytes, maybe 10 or 20 a year. So that drive could last a very, very long time, often way past the warranty.
So getting a drive with way higher TBW than you need is over specification. Paying for endurance you won't use.
Exactly. And the opposite under specification is getting a drive that's maybe too low endurance for your heavy write needs, risking it wearing out prematurely. The sources even give formulas to convert between DWPD and TBW if you need to compare drives. There are also other reliability metrics like UBE unrecoverable bit error ratio that give you an idea of data integrity.
Okay, so endurance is all about the flash wearing out. But what else makes an SSD work? There's more to it than just the memory chips, right?
Oh, absolutely. The controller is hugely important. You can think of it as the SSD's brain. It manages everything where data gets stored, error correction, background tasks, and critically, wear leveling.
Wear leveling, does that do what it sounds like, spreading the wear?
Precisely. Since writing wears out cells, a good controller doesn't just keep writing to the same few spots. It intelligently spreads the write operations across all the NAND cells on the drive as evenly as possible. This is vital for making sure the whole drive reaches its potential lifespan, not just one part failing early.
So a good controller is key to actually getting that TBW rating.
Definitely. Then there's usually some cache or buffer involved.
Right, I see DRAM cache mentioned a lot. What's that for?
Many SSDs have a small amount of very fast DRAM memory on board. It acts as a temporary holding area for data being written or read. This speeds things up, especially for small random operations, and it helps reduce something called write amplification.
Write amplification.
Yeah, it's basically the difference between how much data your computer asks to write and how much data the SSD controller actually has to write to the flash memory internally due to how flash works in blocks. DRAM cache helps minimize that extra writing, which improves performance and endurance.
And some drives use system memory instead, HMB.
Right, host memory buffer. That's common on NVMe drives. Instead of having its own DRAM chip, the SSD borrows a tiny slice of your computer's main RAM to use as a cache. It's a cost-saving measure that still gives a good performance boost.
Clever. And what about those batteries or supercapacitors on some high-end drives?
That's mostly for power loss protection. If the power suddenly cuts, that battery or capacitor gives the controller just enough time to flush any data sitting in that volatile DN cache safely down to the non-volatile NAND flash.
Sure.
Prevents data corruption if the lights go out unexpectedly.
Makes sense, especially for servers and stuff. Okay, so we have the core components. Now, because they don't have spinning disks, SSDs can come in different shapes and sizes, can't they?
They sure can. The old 2.5-inch form factor, the size of a traditional laptop hard drive, is still really common, especially for SATA SSDs. It makes upgrading older systems super easy. Just swap the drives.
Yeah, I've done that. Easy upgrade.
But yeah, without needing space for platters, they can get much smaller. We had SATA for a while, which was like a small card for older, thin laptops.
And now it's mostly M2, right?
M2 is definitely the dominant form factor now for new builds and laptops. It stands for Next Generation Form Factor. It's just a small, gum stick-shaped card that plugs directly into a dedicated slot on the motherboard. Super compact.
And M.2 can be SATA or NVMe.
Correct. That's the key thing about M.2. The slot itself can support either the older, slower SATA interface or the much faster PCIe interface used by NVMe drives. You have to make sure the drive and the slot match protocols.
And those numbers like 2280 or 2230.
Those just tell you the size. 22 millimeters wide by 80 millimeters long is the most common size, 2280. You see 2230, which is shorter, in really small devices like the Steam Deck or some ultra-portable laptops.
Okay. And for maximum performance.
Sometimes you see PCIe add-in cards. These look like small graphics cards and plug into a full PCIe slot. They offer more space for controllers, flash chips, and importantly, bigger heat sinks for cooling on high-performance drives. The sources also mention niche things like DOM's disk on a module for embedded systems and even BGA drives soldered right onto the motherboard.
Lots of options. So let's say you've picked your drive, you've installed it. Now, how do you keep it running optimally? This feels like one of the most practical parts of the sources.
Absolutely crucial. Unlike HDDs where you worry about defragmenting, SSD optimization is different. It's more about helping the drive manage itself efficiently and minimizing unnecessary wear.
Yeah, the number one thing, the absolute foundation, seems to be trim.
Yes, trim is vital for modern SSDs. Think about when you delete a file on an old HDD. The data isn't really erased immediately. The space is just marked as available. But SSDs work differently. Before they can write new data to a block of memory, that block first has to be erased, and erasing is slower than writing.
Okay, so if the drive only finds out a block is empty when it tries to write there, it has to stop, erase the block, and then write the new data. That sounds slow.
Exactly. Trim solves this. It's a command the operating system sends to the SSD immediately after you delete a file, telling the drive, hey, these blocks are no longer needed.
Ah, so the SSD gets a heads up.
Right. And then, during idle time, the SSD's controller can proactively erase those blocks in the background. So the next time your system needs to write data, those blocks are clean and ready to go instantly. No erase delay.
It's like pre-cleaning the workspace so it's ready for the next job.
Perfect analogy.
Right.
TrueRIME keeps write performance high and reduces wear by avoiding some of those unnecessary internal data movements. Windows has supported it automatically since Windows 7. You can also trigger it manually via the Optimize Drives tool. Right-click the drive, Properties, Tools, Optimize. Running that maybe once a week or month ensures trim gets a chance to work, especially if the PC isn't idle much.
And just to hammer this home, traditional defragmentation, the kind you did on HDDs, is a definite no-no for SSDs.
Absolutely. Positively do not run a traditional defrag on an SSD. It does nothing beneficial for performance because access time is instant anywhere on the drive, and it causes a massive amount of unnecessary writes, which directly shortens the lifespan of the drive. Windows knows this and disables traditional defrag on SSDs automatically.
Okay, good. So trim yes, defrag no. What else did the sources suggest for Windows optimization?
Well, there were a few actionable things. One was considering disabling Windows search indexing on the SSD. Indexing helps Windows search files faster, but it involves constant background writing activity. If maximizing endurance is your absolute top priority, you could disable the Windows search service via services.mscc. But your file searches will become much slower. It's a trade-off.
Makes sense. What about HCI mode?
Ah, yes, AHCI. Advanced Host Controller Interface. This is a mode for your SATA controller in the BIOS BFI. It needs to be enabled for SSDs to perform their best. It allows features like NCQ native command queuing, which lets the drive handle multiple commands more efficiently. Definitely want HCI enabled. You can check in Device Manager under ID at top EI controllers.
And enabling it usually happens in the BIOS setup before installing Windows.
Ideally, yes. The sources note that if Windows was installed in the older IDE mode, just switching to AHCI in the BIOS later can cause boot problems unless you make some registry changes in Windows first. So best to set it to AHCI before installing the OS, or follow specific guides carefully if changing later.
Good warning. Okay, what about hibernation and system restore? The sources mentioned maybe turning those off.
Yeah, those are optional too, mainly for saving space and reducing writes. Hibernation writes the entire contents of your RAM to the SSD when you hibernate, which can be many gigabytes per session. You can disable it with PowerCFG off in an admin command prompt. System Restore creates backup points, which also take up space and involve writing data. You can turn it off for the SSD specifically in System Properties, system.cpl, under the System Protection tab. Again, these are trade-offs. Hibernation is convenient, System Restore can be a lifesaver, but they do use space and cause writes.
Depends on your priorities and maybe if you have other backup solutions.
Exactly. And finally, just keeping things updated is always good advice. Keep Windows updated, as Microsoft sometimes tunes things for SSDs, and check for driver updates for your storage controller and device manager, and even firmware updates for the SSD itself from the manufacturer's website. Firmware updates can sometimes improve performance or reliability.
And the sources also brought up a tool, Fortect, for automating some of this.
Yes, the material reviewed mentioned Fortect as a potential tool that could automate tasks like optimization, cleaning junk files, updating drivers, and even repairing system files, suggesting it could help maintain performance.
Okay, so that covers Windows pretty well. How do other operating systems handle SSDs, like Linux or Mac OS? Do they have trim?
Oh yeah, support is generally good across the board now. Linux has had trim support in the kernel for a long time, since version 2.6.33, using the discard command. Most modern Linux file systems like XE4, BTRFs, XFS support it. You generally have two options. Mount the file system with the discard flag for continuous real-time trim, or the more common recommendation is to not use the mount flag and instead run the strim command periodically, maybe daily or weekly via a cron job.
Why periodically instead of continuing?
There were some concerns that issuing lots of small individual trim commands with the discard mount option could sometimes impact performance slightly on some older hardware or configurations. Running strim batches up the trim commands during idle time, which is often considered more efficient. Linux users also often tweak the I/O scheduler, switching from the default CFQ to something like NOOP or deadline is often recommended for SSDs because they handle parallel requests better. And newer kernels have the BlockMU multi-queue block layer, specifically designed for the high parallelism of modern SSDs and NVMe drives.
So Linux users have quite a few knobs to turn. What about Mac OS?
Mac OS also supports trim. It's had it since OS version 10.6.8. For a while, though, it was only automatically enabled for SSDs that came installed by Apple. But starting with OS X 10.0.4, they added a command line tool, TrimForce, that lets users enable trim for third-party SSDs they install themselves. You just run sudo trimforce enable in the terminal.
Good to know they added that. And quickly, ZFS, that file system popular for storage servers.
ZFS can definitely make good use of SSDs, usually as performance boosters rather than the main storage pool, though that's possible too. You can use a fast SSD as an ethlog device to speed up synchronous writes by caching the ZFS intent log, or as an L2 ARC device, which acts as a large, fast read cache for frequently accessed data from the main pool.
Okay, so let's bring it back to reliability as we wrap up. We talked about endurance, the finite write cycles. Are there other ways SSDs can fail?
Well, the lack of moving parts eliminates a whole class of failures you see with HDDs, which is great. But they aren't perfect. Besides wearing out, firmware bugs have occasionally caused issues, sometimes leading to data loss or bricked drives. That's another reason keeping firmware updated can be important, though you always want to be careful with firmware updates.
Right. Follow the instructions carefully. And what about getting data back if something does go wrong? Data recovery.
That's often much harder on an SSD compared to an HDD. Remember trim telling the drive which blocks are deleted. Once the drive's garbage collection process actually erases those blocks, the data is usually gone for good. There's typically no faint magnetic signal left to recover, like on a platter.
So trim, while great for performance, makes recovery much tougher.
Exactly. That, combined with wear leveling spreading data all over the place and potential encryption happening at the controller level, means specialized tools and techniques are needed, and success is far less guaranteed than with many HDD failures. It really underscores the importance of having good backups when you're using SSDs. Don't rely on recovery.
That's a really crucial point to end on. Wow. Okay. We've covered a lot of ground, really pulling from those sources you shared. We went from the basic HDD versus SSD difference through the types of NAND flash and what endurance really means with TBW and DWPD, looked inside at controllers and cache, saw the different shapes like M.2, and spent a good chunk on practical optimization, especially trim for Windows, plus how Linux and Mac OS handle things, and finally, those reliability and recovery considerations.
Yeah, hopefully going through all that, drawing directly on the materials you provided, gives you a much clearer picture of what's going on inside these drives and how to get the best out of them. It's about understanding the tech to make informed choices and keep things running smoothly.
Absolutely. And looking ahead, with SSD tech just charging forward faster NVMe speeds, denser QLC and beyond, maybe new memory types like 3D XPoint becoming more common, it really makes you wonder, doesn't it? How will storage evolve next, and how will that change how we even use our computers? What new optimizations might we need down the road?
It's constantly changing, that's for sure. Definitely an exciting space.
It really is. This whole exploration of solid-state drives, it's just one stream feeding into the bigger river of knowledge we explore here on the All Sorts podcast. If this deep dive lit a spark for you, if it helped clarify some of that complexity using the info you brought to us, then we'd love for you to continue the journey with us. Please subscribe to the All Sorts podcast on YouTube. That's the source where these deep dives originate and where you can find a whole universe of conversations we've already crafted. And connect with us. Find All Sorts podcasts on X, Instagram, and Threads. Share your sources, suggest topics, become part of the current. Your curiosity truly fuels what we do here, and there are so many more insights waiting across all the different podcasts we produce. So please like, share, subscribe, and keep diving deep with All Sorts podcasts.